Hi everyone. In this video, we're going to look at outcome R3, quadratic functions, and you're going to find it in 3.1 and 3.2 of the textbook. Just beware that there are a lot of new key terms here that are important, so make sure throughout the videos you keep track of what they mean so that you know what's going on. Okay, let's get started. The first question I want to look at is just investigating quadratic functions. So first of all, I want you to think about this problem here. You're given a set of squares, and they have different side lengths. So this square is 1 by 1. This is 2 by 2. This is 3 by 3, and so on. Let's record the side lengths of each square on this side. So we've got 2, 3, 4, 5, 6, and 7 units here. And what would be the associated perimeter for each of those? So this first one would be 1 plus 1 plus 1 plus 1. So the second one would be 2 plus 2 plus 2 plus 2, which is 8. The next one's going to be 12. So basically it's 4 times whatever the perimeter is, right? Sorry, 4 times whatever the side length is going to give us the perimeter. So 16, 20, 24, and 28. Now, if we look at this, just as I said, we can come up with the equation y equals 4x. If we graph these points right here, so we're going to have our first point, which is 1 and 4, and just beware of the scale that's given here, okay? We're going to have 2 and 8, then 3 and 12, 4 and 16 will be right here, and so on, right? So you see what's happening? We're going and we are getting a straight line. We can connect all these dots. And if you remember from last year, this is basically a linear equation. So it's a straight line, and it has a slope of 4 and a y-intercept of 0 and an x-intercept of 0. Okay, so now let's look at this next question up here, down here I should say. We are going to look now at the area of each square. And if you remember, area is given by length times width. So if we have a side length of 1, or so let's just record the side lengths here, 3, 4, 5, 6. Now, this case here, if the sides are exactly the same, really, I should write x squared, right? So to get this, I'm going to square my x's. So I've got 2 squared, which is 4, 3 squared, which is 9, 4 squared, 16, 5 squared, 25, 36, and 49. All right, so now let's graph these points, and we're going to look at how it ends up. So the first point I have is, well, if I don't have any length, I don't have an area. And for 1, I'm at 1. And that's right here, okay, because my scale goes up by 2. 2 is going to be at 4. 4 is going to be all the way at 16. So that's up here. Just follow that. 5 is going to be at 25. So that's somewhere in between here. Okay. 6 is going to be 36. So that's right there. And 7 is going to be 49, so that is way up here. Now, if you look real close and you notice that these points from here to here, they don't form a straight line, do they? They actually form a nice, gentle slope. So it's kind of a curve. It is a curve, actually. And we're not really going to look at what happens on this side, but it ends up going back up. And we'll see that in a minute. How are these two graphs the same? Well, they both start at 0. And they increase. Okay, now that's assuming that we're not looking at this point here, right? So if we just look at that, they both start at 0, 0, and they increase from there. How are they different? Well, we can clearly see that the first one is a straight line. So one is linear, and the second one is curved. All right, so we're going to find out soon that this is actually called a quadratic. Okay. So on the next page, the two previous graphs are the same in that they both deal with squares of different lengths. One graph shows the perimeter of a square as a straight line. The other graph shows the area of a square, which we see as increasing at a faster rate. So this is why it makes that curve. How do we compare these two graphs mathematically? Well, the first graph shows a linear relation. It's a function. This means that the biggest exponent on the x is a 1. We don't really see the 1, it just looks like an x. Okay, because it kind of looks tacky when you write the 1. Like, look at this. It looks ridiculous. 3 to the power of 1. See, that looks totally silly. So we don't write the 1. We just leave it as x. The area graph, so the second graph, shows a quadratic function. Okay, so it's nonlinear. It means that there is an exponent of 2 in the equation. So that's what we're looking at, and that's what we're looking at, an exponent of 2 on the x. Okay, so looking at the general form of a quadratic equation, we call it a second degree equation because it has a degree of 2 in the polynomial, where a and b and c are real numbers, and the value of a is not 0. Because if a was 0, what would this look like? Think about it. If a was 0, then this term here would go away, and we'd be left with a linear equation, which is not what we want right now. Okay, so let's have a look at these graphs in more detail. We've got x squared. So if I have 3 as my x, what do? I square it, I get 9. If I have 2 squared, I get 4. 1 squared is 1, 0, 1. Now, negative 1 squared is 1. Negative 2 squared is 4 and 9. So what do we see happening to these negative x values? Well, when they go into the function here, it becomes positive. So my outputs are positive, always. So if we quickly graph this, we're going to get something that looks like this. So 0, 0, that's my 1, because it's going up by a scale of 2, right? Oh, wait, sorry. Hang on. Be careful about the scale. I just told you, and here I am. So that's my 1. This is my 1. So my 1, 1 goes right there. My 2 goes to 4, which is up here. And I've run out of room on my scale, so I'm just going to connect. And the 3 here would go all the way up to 9. So that would be 0.39, and I've run off the graph, so let's not worry too much about that. That's where it's going to go. Look on the other side here, we've got negative 1x. That goes to positive 1 on the y. Negative 2 becomes positive 4. So that goes all the way up there. And with negative 3, we see that, again, it goes all the way up to positive 9. And let's just say it's over here. So that would be the 0.39. Okay, so let's connect these in a nice curve and go up. And one thing I want you to make sure is down here, it's a curve. Don't make it a point or anything like that. It needs to be a smooth curve. This is called, the shape of this is a quadratic. It's called a parabola. Okay? All right. So whenever you see this kind of a shape, it's known as a parabola. It's called a quadratic function, but the shape of the graph is a parabola. Okay, so let's look at this one here. So this equation is in a bit of a different form, and what I want you to notice is the input and output values. So if I input x equals -2, so I substitute that right in here, and then I solve the equation. These are the y values that I end up with each time. And let's have a look at the graph. So this is the graph of it. All right, so -2 is way up at 18. It flies off the graph. Let's look at the points that we can see on the graph. So we've got 0 is at 2. Let's see, what else we got? 1 is negative. One is -3, so that's right there. Okay. And so on. So we've got 3 is at -7, so that's 3, and this is -7. And then what happens to it? It starts to go back up again. So at 4, it goes back up to -6, and we see that it was -6 over here as well. And then it continues. You see these numbers, they're starting to increase again. So right here, this is an important point right here. This is known as the vertex. This is the point at which the parabola changes direction, changes shape. So it goes from decreasing to increasing, and that's where it changes. So the vertex is a very important part. We're going to do a lot with the vertex and think about it in terms of word problems soon. So right here in this graph, it's bottoming out and then it's going back up. So we are going to call it a minimum. So that's a minimum. If this parabola is flipped upside down, it could also potentially be a maximum. Okay. Another important feature of parabolas is something called an axis of symmetry. So it basically bisects the parabola in half. So it cuts it in half. All right, so it bisects it, and then the parabola is reflected. If the parabola is reflected about this line. So what I mean by that is that you could basically take this graph, fold it in half, and see if we, okay, here, I'm going to make this darker so that we could see it through my paper. So this is basically what's happening. And we're taking it on the axis of symmetry here. And we're going to fold it right along that line. And this is basically, if I were to transpose this onto the other side of the paper, I would end up with the exact same shape on that side. So it's basically exactly the same on this side as it is on this side here. That's what that means. So the parabola is reflected about that line. Now, when the coefficient x squared is positive, the parabola opens up, and we see that right here. This parabola is opening up, and the vertex is at the minimum. If the coefficient x squared is negative, then the parabola opens downwards, and its vertex is a maximum point. So if we look at this here, a parabola with a positive a value looks like this, and a parabola with a negative a value looks like this. This would be the vertex. It would be at the minimum, and the vertex here would be at the maximum. All right, now we're going to talk about domain. Now, the domain is the set of all the inputs, and all of the, like any x value you can think of, you can put it into y equals x squared, for instance. So the domain of all parabolas is XER, and you could also write that in interval notation as negative infinity to positive infinity. And remember, our brackets are curved because infinity is not included because we don't know what infinity is. And if we talk about domain, we're going to talk about range as well. Range is a set of all the output values. So that's the y values. It depends on whether the parabola goes up, so whether it opens up, goes to the positive, so it goes to positive infinity, or goes to negative infinity. All right, so it also depends on the position of the y value of the vertex. And let's have a look at a example so that we can get a better feel of all of this. For the following quadratic function, state the following characteristics. Okay, so we're going to look at the graph and we're going to analyze what's happening. So the vertex, that's this point right here, and we're going to read it off the graph. So that's at 1 and 8. The axis of symmetry, it's going to be the x value of the vertex because that's where we can fold it in half and make it symmetrical on both sides, so they're mirror images of each other. So we want to state that as an equation, so x equals 1 in this case. And is there a max or a min? Well, think about it. What happens? If you're traveling along here, you top out here, and then you go back down. So this is known as a max. So it's a max, and the maximum is at, and we state the y value. It's at y equals 8. So we don't really even need to say the y equals. We could just say that it's at 8. The domain, well, that's easy. X is an element of the real set. The range, so we're going to look at the output. So what happens with our y values? Do I ever get any values above 8? I get the value of 8, and I get a whole bunch of values down here, right? I can't get, so my range is going to be y is less than or equal to 8. My x-intercepts is where I cross the x-axis. So this right here we can see is -1, and that is at 3. My y-intercept is right here. That is at 6. All right. So another way that you could look at this is if you set up your table of values and you write in, you figure out each point, and you can see at when x equals 0 and when you get 0 for your y's, you can basically see your x and y intercepts there. You could also see the values where you see right here you've got a -10 and -10. What do you notice about the value of the vertex? So this is the vertex right here, and we end up right in the middle of the, so we're kind of symmetrical, right? This is the halfway point of my parabola. All right, so we see the x-intercepts are that, and the y-intercept is this. Okay, so we're going to draw a vertical line. All right, so that's the vertex. Now, draw a vertical line through the vertex. So go to your graph and draw a vertical line through the vertex. So vertical line right here. Make it a dotted line. All right, just so that, because we know it's not an actual line. We're just trying to show something here. So this is the axis of symmetry that I've just drawn in. And the equation for that is x equals 1. Now, the domain value, well, really, it's all the same for all of these guys. It's x is an element of the reals, and the range, well, we saw that we only have values smaller than or equal to 8 in my y. Okay, so if we look at this in terms of an equation, if the x-intercepts can't be identified from the graph or the table. So if we aren't given a nice graph like we were given, we can solve the related quadratic equation. So we set y equal to 0, and we solve this right here. So how do we solve this? Well, you need to factor it. So basically take out your coefficient of your a. So let's factor out the -2 and continue on just like we did last year with the factoring. So this here, basically we want to figure out what's going to make this 0, and we're going to figure out what makes this 0. Well, x equals 3 is going to make this first bracket 0, and x equals -1 is going to make this second bracket 0. That is how you find your x-intercepts if you don't have the graph. All right, so now we've got the x-intercepts is when the curve crosses the x-axis. That's when y equals 0. And the solution, now here, this is just a bunch of semantics, folks. The solution to the equation, this is the equation, that equation that we solved up there, are the roots of the quadratic. Okay? The zeros of the function are the x values for which f of x equals 0. So this is the solution to the related quadratic equation, ax squared plus bx plus c equals y. Sorry, 0. Which is basically what we solved for here. So see all these words here? Solution to this equation, that's the same as finding the roots, that's the same as finding the zeros, which is the x values for which, well, it's the x-intercepts. That's all it is. You got 1, 2, 3, 4 different ways of saying find the x-intercept. Okay. So try not to get confused with all those words. Just remember them. Okay, so what I want you to do is, here's a question. I want you to press pause on the video, and I want you to give this a try. And honestly, press pause, try it on your own, and then press play again so that you can see what the solution is. Okay, so now that you're back, and hopefully you actually did press pause and try this question, let's run through the solution. We have a parabola with a positive a value, so that means that it opens upwards, and we're going to have the vertex down here. Okay, this is at the part where it bottoms out. Our vertex is the coordinate -3, -8, so it's -3 on the x, and it goes down to -8 on the y. The axis of symmetry is the x value of the vertex. So we say that it's x equals to -3. So you just kind of draw yourself a dotted line to show that that's what it is. Label it like x equals -3. I can't stress enough that you need to write this as an equation. Okay, you can't just write -3. That's not going to be accepted. We've got a minimum because it bottoms out at -8, so that looks for the y value of the vertex. The domain is x is an element of the reals because it just keeps going on and on and on out that way. The range is, well, I never get any values less than -8. I only get values coming out that are greater than or equal to -8. So y is greater than or equal to -8. I can see that my x-intercepts here are -5 and -1. And my y-intercept when my x is equal to 0, so that's right over here, that is 10. And if you notice here, it's real simple. You could just see it if you plug in a 0 here and a 0 there. Well, there you have it, folks. Rewatch the video if you need to, and make sure you do some practice questions. Thanks for coming out.